Good morning, all of you. I am Preeti from BSc Chemistry Honors 3rd year. Today we will read vibrational spectroscopy. So, first section is vibrational energy levels of a simple harmonic oscillator. A simple harmonic oscillator is the one in which the restoring force is proportional to displacement in accordance with Hooke's law. That is, F is equal to minus kx, where k is called the force constant. For such an oscillator, the potential energy is given by half kx square. This is the equation for a parabola. Hence, a parabolic potential energy curve is obtained using the concepts of quantum mechanics. It can be seen that if vibratory motion of the nuclei of a diatomic molecule is taken as equivalent to that of a simple harmonic oscillator, then the vibrational energy is given by the equation E is equal to V plus half h nu, where nu is equal to frequency of vibration and V is the vibrational quantum number with allowed values of 0, 1, 2, 3. Putting mu is equal to C upon lambda, which is further equal to C into mu bar or C omega, where mu bar or omega represents the equilibrium vibrational frequency terms of wave numbers. It can be written as E is equal to V plus half hc omega E. Putting V is equal to 0, 1, 2, 3 in equation 4th, it may be seen that the vibrational energy levels of a harmonic oscillator are equally spaced. For the lowest vibrational level, V is equal to 0, the energy for this level will be given as E naught is equal to half hc omega E. This is called 0 point energy. It implies that even at absolute zero, when all translational and rotational motion cease in a crystal, the residual energy of vibration E naught will still remains, that is, vibrational motion still exists. Next topic is selection rules for the vibrational transition in a simple harmonic oscillator. The gross selection rule for a molecular vibration is that the electrical dipole moment must change when the atoms are displaced. Here note that molecule need not have a permanent dipole. Based on this, the specific selection rule for the vibrational transitions is del mu is equal to del V is equal to plus minus 1. That is, change in vibrational quantum number should be unity. Transition for which del V is equal to plus 1 correspond to absorption, and those for del V is equal to minus 1 correspond to emission. Next topic is vibrational spectra for a simple harmonic oscillator. Applying the selection rule, as the transition can take place between vibrational levels whose vibrational quantum numbers differ by unity, the energy absorbed by a diatomic molecule taking it as a simple harmonic oscillator when the transition takes place from V to V plus 1 level will be given by del E is equal to V plus 1 plus half into hc omega E minus V plus half hc omega E is equal to hc omega E, or del E upon hc is equal to omega E, or del mu bar is equal to omega E. Thus, only one absorption line will be obtained in the vibrational spectrum whose wave number is equal to the equilibrium vibrational frequency of the diatomic molecule. Otherwise, as the vibrational levels are equally spaced, any transition from any V to V plus 1 will give rise to same energy change, and hence only one absorption line is expected. Further, at room temperature, as most of the molecules are in lowest vibrational level with V is equal to 0, therefore the transition taking place are from V is equal to 0 to V is equal to 1. The frequency thus observed is called fundamental frequency. These spectra are observed in IR region. Next topic is types of molecules showing vibrational spectra. As already mentioned, the gross selection rule for a diatomic molecule to give a vibrational spectra is that the dipole moment of the molecule must change when the atoms are displaced due to vibration. The condition required is only the change in dipole moment, and the molecule need not have a permanent dipole moment. For example, in case of homonuclear diatomic molecules like H2O2 and 2, which have only stretching motion and no bending motion or vibration, the dipole moment does not change during vibration. Hence, these molecules do not give vibrational spectra, that is, they are said to be infrared inactive. On the other hand, heteronuclear diatomic molecules like HCl, CONO, and polyatomic molecules like CO2, water, methane, and ethene, which show change in dipole moment in some mode of vibration, give vibrational spectra and are said to be infrared active. Next topic is vibrational energy levels of an enharmonic oscillator. When a molecule is undergoing simple harmonic oscillations, the restoring force of the harmonic vibrations is directly proportional to the displacement, and the energy of the harmonic oscillator is given by E is equal to V plus half Hc omega E, where V is the vibrational quantum number, which may be 0 or an integer, and omega E is the equilibrium frequency of vibration of the oscillator, that is for small displacements. Strictly speaking, the movement of a real oscillator is not perfectly harmonic. This is because as the displacement increases, the restoring force becomes weaker, and for large enough amplitude of vibration, the atoms of the molecule must fall apart. That is, the molecule must dissociate into atoms. Such a real oscillator is said to be an harmonic oscillator. P.M. Morse in 1929 suggested that the above equation has to be modified for an enharmonic oscillator by including one additional term known as EV is equal to V plus half Hc omega E minus V plus half whole square Hc Xc omega E, where Xc is called enharmonicity constant. Putting V is equal to 0, 1, 2 in equation 1 and 2, the energy levels of the harmonic oscillator in the enharmonic oscillator may be obtained. It may be seen that whereas the energy level of a harmonic oscillator are equally spaced, those of enharmonic oscillator are not equally spaced but fall more closely together as the quantum number increases. Further, whereas the potential energy curve for harmonic oscillator is a parabola, that of enharmonic oscillator is shown in figure. Next topic is selection rules for the vibrational transition of an enharmonic oscillator. Whereas the selection rule for the harmonic oscillator is del V is equal to half plus minus 1, the selection rule for enharmonic oscillator are del V is equal to plus minus 1, plus minus 2, plus minus 3, and so on. Thus, all types of vibrational transition are possible. However, the transition from V is equal to 0 to V is equal to 1 is found to be more intense due to greater population of these energy levels and is called the fundamental absorption. The transition from V is equal to 0 to V is equal to 2 has a very weak intensity and called the first overtone. The transition from V is equal to 0 to V is equal to 3 has still weaker intensity and called as second overtone, and so on. Vibrational rotational spectra. Pure vibrational spectra are obtained only for liquids, whereas rotational motion is hindered due to interaction between the liquid molecules. However, in case of gaseous molecules, as the energy required for rotation is much less than that required for vibration, the vibrational motion is always accompanied by a rotational motion, and hence we do not have a pure vibrational spectra. Instead, we have a vibrational rotational spectra lying in the IR region. As rotational motion and vibrational motion takes place independent of each other. Applying Oppenheimer approximation, the total energy of the molecule may be taken as the sum of rotational energy and the vibrational energy. Thus, E total is equal to ER plus EV, or it can be written as EVJ is equal to EJ plus EV. Expressing in terms of wave number, it can be written as mu bar is equal to mu J plus mu V. From equation 4, Vj V mu bar J is equal to Bj into J plus 1. Mu bar is equal to V plus half omega E minus V plus half whole square Xc omega E. Substituting these values in equation 15, we get mu bar is equal to Bj into J plus 1 plus V plus half omega E plus V plus half whole square Xc omega E, where mu bar Vj represents the wave number of a rotational level with quantum number J in the vibrational level with quantum number V. From equation 6th, it is clear that in same vibrational level there will be number of rotational levels corresponding to J is equal to 1, 2, 3 and so on when a transition takes place from a level with quantum number V and J to a level with quantum number V dash and J dash. The energy changes expressed in terms of wave numbers will be given by del mu bar is equal to Bj dash into J dash plus 1 plus V dash plus half mu E minus V dash plus half whole square Xe omega E into Bj into J plus 1 plus V plus half omega E minus V plus half whole square Xe omega E. Restricting to the transition from V is equal to 0 to V dash is equal to 1, we get Bj dash into J dash plus 1 plus 3 upon 2 omega E minus n upon 4 Xe omega E minus Bj into J plus 1 plus half omega E minus 1 upon K 1 upon Xe omega E, which is further equal to Bj dash J dash plus 1 minus J into J plus 1 plus omega E minus 2 Xe omega E, which is further on solving will give B into J dash minus J into J plus J dash plus 1 plus 1 minus 2 Xe into omega E. Putting 1 minus 2 Xe omega E is equal to omega naught, we get del mu bar is equal to omega naught plus B into J dash minus J into J plus J dash plus 1. For transition with del J is equal to plus 1, that is J dash minus J is equal to plus 1 or J dash is equal to J plus 1, del mu bar is equal to omega naught plus 2B into J plus 1, where J is equal to 0, 1, 2, 3. The second is for transition with del J is equal to minus 1, that is J dash minus J is equal to minus 1 or J is equal to J dash plus 1, del mu bar is equal to omega naught minus 2B J plus 1, where J dash is equal to 0, 1, 2, 3. Combining equation 10 and 11, we get del mu bar is equal to omega naught plus 2bm, where m is equal to J plus 1 and m is equal to minus J dash plus 1 in equation 11th, and J is equal to 1, 2, 3. This means that in equation 12 m is equal to plus minus 1 plus minus 2 plus minus 3 and so on. The nature of the vibration rotation spectra can be predicted from equation 12. As m is equal to 0, therefore line corresponding to frequency omega naught will not appear in the spectrum. This wave number is called band center or band origin. As m is equal to plus minus 1, plus minus 2, plus minus 3, it follows the spectrum will consist of equally spaced lines on each side of the band center with spacing equal to 2b between any two adjacent lines. Keeping in view the selection rule del J is equal to plus minus 1, the absorption transitions take can that can take place from level V is equal to 0 to V is equal to 1, and the corresponding lines obtained in the spectrum may be represented as shown in figure. PQR branches of the vibration rotation spectra. In equation above, omega naught represents the fundamental frequency. This is called the center or origin of fundamental band. First is for del J is equal to minus 1. Lines with frequency lower than the fundamental frequency are obtained. These lines are called P branch of the spectrum. For del J is equal to plus 1, lines with frequency greater than the fundamental frequency are obtained. These lines are called R branch of the spectrum. For del J is equal to 0, that is when a vibrational transition occurs without accompanied by rotational transition. Example in case of NO, del mu bar is equal to omega naught. That is, a single line should be obtained at the center. In actual practice, as the rotational constants of the two vibrational levels are slightly different, a cluster of closely spaced lines appears at the center. This group of lines is called Q branch of the spectrum. When this type of transition is forbidden, a gap appears at the center. Next topic is intensity of the lines in P and R branches. It is important to note that intensities of lines in P and R branch are shown in figure will be observed only if the resolving power of spectrometer is very high. If the resolving power is not so high, then the spectrum obtained is shown in figure 3.26. Next topic is structural information from IR spectra. By carefully locating the band center corresponding to the transition V is equal to 0 to V dash is equal to 0 fundamental transition, and the transition V is equal to 0 to V dash is equal to 2, that is first overtone, the value of the frequency omega E and the inharmonicity constant Xc can be obtained. Also, the frequency separation any two adjacent lines of the P branch or R branch gives the value of 2V. Knowing the value of omega E and Xc, the force constant and dissociation energy of the molecule can be calculated, and knowing the value of B, the moment of inertia and bond length of the diatomic molecule can be calculated as explained below. Calculation of moment of inertia and bond length. As discussed in rotational spectra, B is equal to h upon 8 pi square Ic. Frequency separation del mu bar is equal to 2B, which is further equal to h upon 4 pi square Ic. Thus, knowing the frequency separation, the moment of inertia, and hence the internuclear distance, that is bond length of a diatomic molecule, can be calculated. Calculation of force constant. Taking the simple case where a diatomic molecule may be considered as a simple harmonic oscillator, that is an oscillator in which restoring force is directly proportional to the displacement. In accordance with Hooke's law, we have F is equal to minus kx, where x is the displacement and is equal to the distance to which atoms have been stretched, minus equilibrium distance between the atoms, that is x is equal to minus r minus re. K in equation 13 is called force constant. Thus, if x is equal to 1 centimeter, K is equal to minus F. Hence, force constant may be defined as the restoring force per unit displacement of a harmonic oscillator. It is found to be related to equilibrium vibrational frequency omega E. According to the equation, omega is equal to half pi into K upon mu under root, where mu is the reduced mass of the system. To calculate K, equation 14 can be rewritten as K is equal to 4 pi square omega E square into mu. K is equal to 4 pi square omega E square into m1 plus m2 upon m1 into m2 upon m1 plus m2, where m1 and m2 are the masses of oscillating atoms. Thus, knowing vibrational frequency omega e and the masses of the atoms of diatomic molecule, the force constant K can be calculated. Note that omega e is in second inverse. However, a problem arises with the polyatomic molecules because each bond has different force constant. This problem is solved by assuming that a force constant is associated not only with bond but also with every bond angle. A detailed study of such molecules is beyond the scope of present book. The force constant for a number of bonds have been determined. It is found that force constant increase almost directly with the multiplicity of the bond. This is illustrated by some values given below. Bond that is C single bond C has force constant 4.6 into 10 raised to power 5 dynes per centimeter. Carbon carbon double bond has force constant 9.5 into 10 raised to power 5 dynes per centimeter, and carbon carbon triple bond has force constant 15.8 into 10 raised to power 5 dynes per centimeter. Thus, the multiplicity of the bond can be predicted from the values of force constant. For example, the force constant for C triple bond oxygen in carbon monoxide is 18.6 into 10 raised to power 5 dynes per centimeter, whereas the force constant for C double bond O in carbon dioxide is 15.2 into 10 raised to power 5 dynes per centimeter. This results this result confirms that CO2 has a resonating structure containing both carbon oxygen double and triple bonds. Calculation of equilibrium dissociation energy. Equilibrium dissociation energy of a diatomic molecule is given by D is equal to omega E upon 4xe. This is the dissociation energy when it is measured from the bottom of the Morse potential energy curve. The true dissociation energy is however measured from ground level and is given by d naught is equal to omega e upon 4xe minus half of omega e into 1 minus half of xe. Next topic is normal modes of vibration of polyatomic molecules. A diatomic molecule has only one mode of vibration, that is oscillation of the two atoms along the line of centers, and so it is given as comparatively simple spectrum. A polyatomic molecule consists of nitrogen atom n atoms, has 3 n degrees of freedom, that is the coordinates required to specify the position of all the n nuclei. Out of these, there 3 are translational degrees of freedom. Further, if the molecule is linear, there are 2 rotational degrees of freedom corresponding to 2 independent mode of rotation, one about x-axis and other about y-axis. The remaining 3n minus 3 minus 2, which is equal to 3n minus 5, are the vibrational degrees of freedom. On the other hand, a non-linear molecule has 3 rotational degrees of freedom corresponding to rotation about 3 mutually perpendicular axes. So the remaining 3n minus 3 minus 3, which is equal to 3n minus 6, are vibrational degree of freedom. The number of vibrational degree of freedom as calculated above correspond to normal modes of vibration of polyatomic molecule, as otherwise the vibratory motion of a polyatomic molecule may be very complicated. A normal mode of vibration satisfies the following two conditions. First is the nuclei move in phase, that is, the nuclei pass through the extreme of their motion simultaneously. Second is the motions of the nuclei are such that the center of mass does not move and the molecule as a whole does not rotate. The above two conditions imply that different atoms move different distances. Each mode of vibration has definite frequency. Further, two or more different modes may have the same frequency. They are then said to be degenerate. The various modes of vibration are either symmetric or antisymmetric. In case of linear molecules, these may be further stretching or bending. In case of a triatomic linear molecule like CO2, normal modes of vibration is equal to 3 n minus 5, which is equal to 3 into 3 minus 5, which gives 4. One of these mu bar, one is symmetric stretching vibration. The second mu 2 bar is asymmetric symmetric stretching vibration. The third and fourth are bending but degenerate, as they differ only in the fact that motion takes place in two mutually perpendicular planes. It may be noted that stretching vibrations has higher frequency than the bending vibrations. It is usually so because larger force is required to stretch a bond than to deform the bond angle. On the other hand, in case of triatomic linear molecule like water, normal modes of vibration are three. All these are non-degenerate. Two of these are symmetric while the third is antisymmetric. Another way of classification of different vibrational modes is on the basis of direction of change of dipole moment of the molecule accompanying the vibration. If there is no change, that is, the direction remains parallel to axis of symmetry of molecule, it is called parallel vibration, and if there is a change which is in direction perpendicular to axis of symmetry of molecule, it is called perpendicular vibration. Thus, in case of CO2, mu 1 bar and mu 2 bar are parallel vibrations, whereas mu 3 bar is equal to mu 4 bar is perpendicular vibration. Similarly, in case of water, mu 1 bar and mu 2 bar are parallel vibration, where mu 3 bar is perpendicular vibration. Further, for a symmetrical linear molecule like CO2, which does not have any dipole moment, the symmetrical stretching does not produce any dipole moment. Such a vibration is not active in IR. On the other hand, the vibration mu 2 bar and mu 3 bar of CO2 as well as the all three modes of vibration of water are accompanied by change of dipole moment during vibration. Therefore, all these are active in the IR spectra. Isotopic effect on the vibration rotational spectrum. Taking the example of vibrational rotational spectrum of HCl, it is found that if the resolving power of the spectrometer is high, each individual line of the spectrum is found to consist of doublets having a wavelength difference of about 27 angstrom. This splitting is due to the presence of two isotopes of chlorine, chlorine 35 and chlorine 37 isotopes in HCl. These isotopes with different masses results into different moment of inertia and fundamental frequency of vibration for HCl 35 and HCl 37. Hence, they produce splitting of the lines. Next topic is vibrational frequency of different functional groups. The vibrational spectra of all polyatomic molecules are very useful for the identification of organic compounds or for testing the purity of a compound by comparing its infrared spectrum with that of the pure compound. As already explained, a molecule made up of n atoms has 3n minus 5 and 3n minus 6 normal modes of vibration. These vibrations may be divided into two parts with skeletal vibrations and group vibrations. The skeletal vibration involve all the atoms of the molecule, whereas group vibration involve the vibration of a small group of atoms whose atoms have more vigorous vibrations than the rest of the atoms. These vibrations takes place when the molecule absorbs energy in the infrared region. The energy thus absorbed are usually expressed in terms of wave number centimeter inverse. It is observed that skeletal vibrations takes place when the absorption of energy is up to 1500 centimeter inverse. They are characteristic of the molecule as a whole, that is, whether it is linear, branched, or has pentaid structure. This part of the spectrum is called fingerprint region. However, certain groups of atoms, irrespective of the molecule in which they are present, absorb at the particular wave number to exhibit group vibration. A few functional groups show absorption in the fingerprint region. Thus, they give rise to characteristic absorption bands in the spectrum. The frequency in terms of wave numbers at which different functional groups show absorption are shown in a table for some very common functional groups or groups of atoms. Thank you.